Assalamualaikum warahmatullahi wabarakatuh, and very good day to everyone. So we are from group 3 in the subject of quality control, and today we are excited to present of our group reflection video based on our recent visit on the Festival of Ideas Negeri Sembilan 2025. The event was held on the 29th October 2025 at University Sains Islam Malaysia, USIM, and it brought together creative minds from various backgrounds, including students, researchers, and innovators who showcase their latest projects and ideas. Our main objective during the visit is to observe how innovation and quality control work together. Specifically, we focus on identifying how quality control QC and total quality tools TQ will apply to improve process, product, or system in the showcase innovation. Quality tools are essential in ensuring that innovation are not only creative but also reliable, consistent, and ready for real-world application. By observing how these tools were used, we gain valuable insight into how innovation can be strengthened through systematic quality management. So in this video, we will share one innovation that truly impressed us, analyze the quality tools applied or suitable for it, and reflect on the lesson we learned about QC and TQ in supporting continuous improvement and innovation.
From the exhibition, the innovation that we chose was a project titled Enhancing Antibacterial Properties Using Silver Dope Zinc Oxide Nanoparticles. Next, the project also highlights several important problems in the biomedical and orthopedic field. These include the high risk of implant-associated infections, the formation of biofilms, and the growing issue of antibiotic resistance. All these factors make current implant materials less effective and increase complications after surgery. To address these problems, the researchers developed silver dope zinc oxide nanoparticles through a controlled precipitation method. From the results shown like FISM images, XRD patterns, FTIR analysis, and disk diffusion tests, the material demonstrated strong antibacterial activity, improved surface reactivity, and good biocompatibility. This shows that the innovation is not only effective but also stable and suitable for biomedical use. From a quality perspective, this project also shows where total quality tools could be applied. For example, a fishbone diagram would be useful to identify the root causes of implant infections, whether they come from material issues, handling procedures, or environmental contamination. A control chart also helps monitor consistency in antibacterial performance by tracking inhibition zone results across different trials. Overall, the innovation has strong potential for applications such as wound dressings, orthopedic implants, dental coatings, and other infection-resistant medical devices. It clearly shows how scientific development and quality improvement can work together to enhance patient safety.
To ensure the success of the project enhancing antibacterial properties using silver dope zinc oxide nanoparticles, to maintain consistent quality, the team applied total quality tools through the process. This tool allows the team to identify problems efficiently, improve workflow, and ensure that every experiment met both scientific and quality standards. In this reflection, the focus is on two main tools, the PDCA cycle and the cause and effect diagram, and how they support innovation, precision, and continuous improvement. The first tool applied by the team was the PDCA cycle, which stands for Plan, Do, Check, and Act. It helped the team organize experiments systematically and minimize error. During the plan phase, the team set clear objectives for synthesizing silver dope zinc oxide nanoparticles with enhanced antibacterial activity. Planning parameters such as temperature, concentration, reaction time, and steering method. In the do phase, the experiment will carry out carefully monitoring each step for consistency. The check phase involves analyzing SRD, SEM, and antibacterial test data. The team assess whether a nanoparticle achieves particle uniformity, correct crystalline structure, and optimal antibacterial performance. Finally, in the act phase, methods were refined, adjusting temperature or concentration to improve nanoparticle quality. This continuous cycle ensures that each Each experiment contributes to learning and increase precision and efficiency. Second TQ tool applied was the cause and effect diagram, also known as the fishbone or Ishikawa diagram. The team used it to identify factors affecting nanoparticle quality. The main categories included material, method, machine, and manpower. For example, under material, they evaluated precursor concentration and raw material quality. In method, reaction time, temperature were assessed. And for machines, focus on equipment, accuracy, and steering stability. Finally, manpower emphasized consistent handling technique by the team. Visualizing this factor allowed them to trace the root cause of quality issue and take the preventive measure early. As the result, every step of the experiment became more organized, transparent, and continuously improvable.
Next, moving this brilliant innovation from the lab to a sustainable business require additional quality control, specifically through total quality tools. While the researchers have proven their concept, they need to prove process stability for the commercial potential. Therefore, we propose implementing control chart, which is the X bar and R chart. And don't let the team confuse you. These are the statistical quality detective. The two charts work like a team to monitor the product's quality. The X bar chart is the average checker. It ensures the average strength of the antibacterial coating, which is the zone of inhibition size, is always meeting the exact quality standard we established in the lab. And the R chart is the consistency checker. It guarantees that the quality is uniform across the entire batch to make sure no single nanoparticle is too weak or too strong. This tool is important for total quality because it acts as an early warning system. Instead of waiting for the batch to fail, this chart detects tiny issues before a single batch product is fully created. Most importantly, implementing this chart gives us the statistical proof of stability that regulators demand. This is the most important step that secures our regulatory approval and enables the team to confidently achieve their regional market expansion goal, transforming a research into a high-quality, reliable medical product.
For my personal reflection during the visit at the festival of IDEA, I learned that quality control is not only about inspection. It's about maintaining consistency and reliability throughout the process. The researchers at USIM show how systematic quality tools ensure valid results and trustworthy innovation.
So, by observing the PDCA cycle in action helped me understand how continuous improvement works in practice. Even small changes, when planned carefully and tested step by step, can make a big difference. I also learned that teamwork and clear communication are essential because solving problems together leads to better results. Overall, this experience taught me that quality comes from paying attention to details, learning from mistakes, and always looking for ways to improve.
Through this project on enhancing antibacterial properties using silver dope zinc oxide nanoparticle, I gained a deeper understanding of how closely innovation is tied to quality control. Nanoparticle is not just about synthesis but about ensuring consistency at every stage, for selecting the right doping ratio to monitoring temperature, pH, and reaction time. Using total quality tools like the fishbone diagram and the PDCA cycle also help them analyze problems more critically. When samples show the variation in antibacterial activity, this tool guides us to identify root cause and chart. Overall, this project taught me that quality and innovation must move together. Strong antibacterial performance can only be achieved when scientific creativity is supported by the systematic QC and well-structured research procedure.
From this project, I learned that innovation isn't just about having creative ideas. It also needs proper quality control. Tools like the PDCA cycle and fishbone diagram help the researcher improve their process and result. I saw how small changes like adjusting material or methods could make a big difference. This experience taught me that quality comes from planning, teamwork, and always looking for ways to improve.
For me, what I have learned is that scientific discoveries by themselves are not sufficient enough to create real change. For high-tech medical innovation like this, the real step to success isn't just proving the product works once, but proving it's statistically reliable every single time. It taught me that total quality tools are the bridge between a great idea in the lab and a safe, trustworthy product on the market.
To conclude, our group learned that innovation and quality control go hand in hand. Tools like the PDCA cycle and fishbone diagram are not just for industrial use, they are also powerful in research too. As a proposal, we plan to apply the fishbone diagram in future class projects. For example, to identify the root causes of issues in a physics experiment. With strong collaboration and a clear understanding of quality tools, we believe every project can be more organized, effective, and impactful. Thank you for watching, and we hope our reflection inspire others to embrace quality in every step of innovation.